Okay, I think it's working. So, let's start somewhere. I want to learn about quantum computing. I know nothing about the subject. I know so little that I often forget about the name of it. What do I know? I know it doesn't use bits, it uses qubits. I know. I don't know. I believe it is based on light, or I don't know. I have no clue what it is. And don't want to have assumptions. So, some background for those that don't know me. Um, I'm in cybersecurity for like 15 years or so. Um, I've worked in the blockchain community since 2017, so about 7 years. Um, and recently, for the last 2 years or so, I've been using AI and building stuff with AI. And I've always been fascinated by emerging technology. Funny enough, I get pretty bored with it. Um, I loved blockchain for a long time. I co-founded two startups in the blockchain area, both quite interesting. um, I fell in love for it for a long time. I lived from crypto for 3 years. Um, but then I got so bored on fraud and scams, and it's boring. I was scammed multiple times. I had a great amount in Cryptopia when it was hacked. Um, I made mistakes with wallets. Um, I made great things with wallets. I recovered some wallets. uh, Not everything is bad. Actually, the majority is quite interesting. I liked crypto for a long time, but then I got bored from it. And then AI. I like AI. I think AI is fascinating. I'm in the in love phase with AI. I've been building stuff with AI. I have 3 running projects currently with AI. Both of them are pretty interesting in areas that I like very much, namely ad tech, security, cybersecurity, slash compliance, and infrastructure. Those are probably the 3 areas that I like the most. And the other area that I probably will do something is on food, as I love food. I wanted some years ago to open a restaurant, and I went through that venue, through that journey. Then COVID came, so I decided not to go even further. But I was moving in that path. I love food, and I wanted to have a restaurant for a long time since I'm a kid, basically. So these are probably the 4 main areas that I like the most: ad tech, food, compliance slash cybersecurity, law, and infrastructure. Infrastructure, I mean IT infrastructure, not physical infrastructure. Actually, I don't enjoy that much physical infrastructure. I had I'm schooled from a an industry from petroleum industry. I don't know if that's correct or not. Um, and I moved away from it because I don't enjoy that much the field, the physical field, and yeah, I don't enjoy that much. But I love infrastructure and I love IT infrastructure. And speaking of which, I believe, and I'm eager to say that I'm not wrong, that quantum computing will be the next major thing. I just read something today about a biological computer with 16, I think, neurons. And I truly believe that is something that is quite interesting and revolutionary. I made some fun of it, like having a biotech girlfriend. Um, and I think that is some path that eventually will become quite interesting. Though I believe it's quite immature yet. Well, not that immature, I'd say, because they are already selling to public, so there's a product out there that is working. I might look into it just for the sake of curiosity, but regarding knowledge, I think AI and quantum will be the main subjects in 10 years. Possible blockchain too. Not sure about that. Not sure at all about that. I would say that uh, some kind of post quantum cryptography will lead web and either break blockchain or make it completely different. I don't know. Even though I've been in this for a long time, I don't see much value in blockchain, to be honest. I think it is pretty attached to crypto, and there is not much value in the technology yet. Probably it will be. I'm sure someone will have a great idea that is inherently attached to blockchain, and that will create a new way of doing stuff. Um, I'm not sure if that's Web3. Actually, if we look back in time, Web2 wasn't created. It emerged from platforms like Facebook and so forth. The concept that we create the content, everybody can create the content. You don't need to have a web page or infrastructure. It's quite revolutionary. So the difference between Web 1 and Web 2 is larger than those two to Web 3. The concept that you own your data, it's very interesting in paper, but I don't believe it holds that much value actually, except for money, except for value itself, like real asset NFTs and crypto, but not much than that actually. one of the projects that I had, one of the startups that I had was Vivil, and we created a no-code smart contract builder. And to achieve that, we created a domain-specific language, a DSL, sorry, which was visual, so people could drag and drop boxes and create smart contracts without coding. So we had a no-code platform. The product was indeed interesting, and we had quite great players with us. We had 5 top blockchain audit companies working with us. Um, and when I was asked by people about what's a smart contract and why is that relevant, I I had a problem to explain the need for it and the value for it for regular people. Sorry, it's not regular people. It's not the most pretty way to say so. People outside Web3. Um, because everybody knew about Bitcoin, at least the name of it, but no one knew about smart contracts or the blockchain itself. So it was quite hard to explain what's the beauty in a smart contract and why it has value on itself. And that's the main issue in blockchain. Still in the same subject, um, I was invited years ago to speak in a conference about blockchain. And I was asked what is necessary in blockchain to make it mainstream. And my answer was quite interesting, but sorry to say so, it doesn't sound that humble. But I honestly think so. It's an interesting answer, and I still hold to it because my answer was that it makes no sense to speak about blockchain and make it mainstream. It makes as much sense as ask how are we going to make relational databases or non-relational databases mainstream. People don't care. People don't care if Facebook uses MySQL or CouchDB. People don't care. It's irrelevant. The technology part of it, the infrastructure part of it, it's completely irrelevant for the end user. And blockchain slash crypto is very techy, and people still hold on to the concept of having a great technology and ignores the need for it, the market need for it. So people create business models around the technology for the sake of money and not for the sake of usability. And I haven't seen much in blockchain that actually adds value except on crypto. And regarding crypto, I think the only value in crypto is actually the the, the borderless transactions, not the transparency, not the anonymity. I actually think that's more problematic than advantageous for today's society. But the borderless ability to transfer money is indeed interesting, especially considering countries in which money is um, pretty instable, unstable, non-stable, um, or countries in which the the money exporting is problematic, meaning that it's hard to transfer money from the countries to another. For example, from Angola is very hard, as I was told so, to take money off Angola. Um, but international payments is much more efficient with crypto than with efficient, not in terms of energy, of course, but everything around except energy is much more interesting with blockchain, with crypto, than with regular money. Um, Especially when considering the ability for some infrastructure or some banks to prevent the reception or the transfer of those assets. And I was blocked quite a few times, especially with PayPal. Actually, I don't use PayPal anymore because of that. And blockchain prevents it, and blockchain allows international transfer in minutes, and that's fascinating. But other than crypto, I think it's completely useless. Maybe NFTs, if you want to create real assets with it, probably using real life contracts attached to smart contracts. Um, I had a concept. I still have a concept that I've worked for for the sake of creating a POC for it, which is using blockchain for auditing, for a compliance auditing, and the concept is quite interesting. The way it is modeled, it's 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 very different from how it's done today, and I believe blockchain is great for it, but it's not a necessity. A Web2 platform can do the same. Just for the sake of decentralization, it doesn't need to be a decentralized infrastructure to be decentralized. For a real life scenario, in a theoretical approach, indeed it must be, but in a real life scenario, it's agnostic. It, it's irrelevant. So, why quantum cryptography? Quantum computing? Because I truly believe in quantum cryptography. I think that's that's an absurd leap in technology, allowing you to transfer information from one place to the other without the ability to being eyes dropped is among us. From my background in cybersecurity and hacking, I started as a hacker. Even though I've never called myself a hacker, I now look back and I hacked more when I was a kid than I do today. Uh, the ability for you to transfer information from one place to the other without having middleman eye dropping information is fantastic. And as I'm believing so, the communication is transferred at the speed of light, which is absurdly faster than what we have currently. I don't know what's the maximum theoretical throughput of fiberglass, but I believe that anywhere in the world, a communication between two quantum computers is borderline instant. I believe. I've never read fully about it. And that's awesome. Um, One thing that I fear about quantum computing is that I truly believe that the reason we think quantum computing, especially quantum cryptography, is completely revolutionary is because science lacks a fundamental knowledge in the quantum stuff. This is philosophy, pure philosophy. I don't know enough to to argue about it. It's just pure philosophy. I believe we lack some knowledge that eventually we'll gain. We slash science, as in science, I mean. That once we know about some uncertainties that we currently believe are core in quantum, that will break quantum cryptography instantly. Until then, and that may happen tomorrow, that may happen in 1,000 years, that may possibly never happen, and actually quantum is this strange word. But I believe so. But while it doesn't happen, we will definitely use it. And I can foresee some near future. Near, I mean like 20 years. I don't believe it will be earlier than that, in which we'll have some sort of micro quantum computer in robotics, and they communicate with a biocomputer in some kind of data center instantly, or at least faster than current technology for sure. But I believe that the bottleneck will not be the communication, but the processing. I think that bioprocessing will be slower than the communication itself. I can totally see a near future with some kind of things like that. So yeah, I've been speaking for a long time. I want to have a countdown because I want to have a ouch. Ouch. I hurt my leg quite badly though. Ouch, Charlie. It's still hurting. Do you remember those memes? Charlie bit me. Ouch, Charlie. Ouch, Charlie. Ouch, Charlie. Charlie bit me. Yeah, I want to have a countdown, but I don't know how to make a countdown. Can I have like a web countdown? Can I? I surely can. I'm sure there's some web countdown over somewhere. Countdown. Countdown timer? No, I don't want GDPR stuff. Oh, great, Google has one. Like stopwatch. Yeah, stopwatch is nice. Yeah. Mm. Can I add this to the screen? Let me do something. Window capture. This. Okay. And now this and this. Yay, it works. And now I want this to go just barely down. I want this to change name. Countdown. I'm working in OBS, by the way. I'm just trying to make it work. So crop from the left, from top, right, from right, all right, and from bottom, and from bottom. And now I want a chroma key on white. Custom color, white. Perfect, it works. But I don't want any similarity, and I don't want smoothness. Why not working? I want this to be white. Opacity. Contrast. Why you're not working? Can I just make something like this? Why does it disappear? This is similarity at 0. Why you're... Makes no sense. Excuse me. Sorry. Contrast, brightness, gamma. White. I want white. I want white, and I don't want any similarity. Neither smoothness, neither key. I don't understand this. Ah, great. I was doing something odd. I don't know what. Contrast. Absolute. Ooh, great. And brightness? Ha ha ha. Yeah, I love it. Gamma? No need for gamma, I think. Yeah, no need for gamma. Alright, so this can be like here. I want this must be in a specific city. I mean, place. Yeah, probably around here. Maybe I should make it like the same space from top. I want to cut it a little bit, and also from bottom. Yeah, because I think this won't be used that much. I should probably also add some background to it. Can I add a background to it? Can I add a background? I don't want to do this time. Actually, this is taking quite a long time already. Yeah, maybe here. Maybe down here. Can I add like contrast? Brightness. The goal was to have brightness. Brightness. Yeah, that's alright. Yeah, that's alright. I like it here. Yeah, alright. So let's start the countdown. Can I start just by clicking here? Will it work? Why is it not working? Because it's a timer. I don't want a timer. Why? Oh, funny. Funny. Real funny. Real funny. Real funny. Alright. Yeah, that's good. Okay. So we have a timer. Dude, this is too fast. I don't want milliseconds. I want like 2 hours. 2 hours. And that's more than enough. Right. Yeah, 2 hours is more than enough for what I want. So this is 10 o'clock. So at midnight I should be done. So starting right now. So what's my goal? My goal is to document my journey in quantum computing. So first and foremost, I'm going to Gemini. Can I reduce? Oh, no, it's going to. Oh, I don't know what was there. Yeah. Okay. It's alright. Just for the sake of curiosity, I started before having the idea to make this live, teaching atomic computing. Just for you to know that I sometimes forget that this is called quantum computing. So yeah. What's the goal of it? We want to learn, or I want to learn about quantum computing. As I don't know anything about that, I need your guidance. I like to start with some introductory YouTube videos. So please provide some that explain the science behind it and the ports used in quantum computing from reputable reputable sources. This is definitely not the prettiest prompt, but I think it will work. It might. From Ted, from Qiskit. Okay, Qiskit. I think it's an app or a framework for quantum computing. From Veritasium, I'm pretty sure I've seen this video before. I'm pretty sure I did. I believe it's in collaboration with IBM. And speaking about IBM, I played with quantum computers in the past from IBM Cloud, like 10 years ago or so. And it was literally a play. I opened a platform that I could link ports and have some results, but I understood zero from it, so I'm completely fresh in this. So I don't want to lose time. So what I'm going to do is know if Gemini can make a summary. Yeah, I've seen this. Make a summary of each of those videos. Please make a summary of those videos. I'm not sure if it can do this. It does. Great. I didn't know about it. I don't often use Gemini. I mostly use GPT, and most recently Anthropic's Claude, because I like the text of Claude better than GPT, but definitely I'll use way more GPT than any other AI or text AI. So yeah, quantum computing in 5 minutes. Quantum computing explained. Quantum computer. The video from Simple-Learn. By Simple-Learn explains quantum computer and their potential applications. Quantum computers are a new type of computers that use the principle of quantum mechanics for performing calculations. They have the potential to revolutionize many fields, including medicine security. For example, quantum computers could be used for create unbreakable encryption keys. Yeah, again, for TED is quite broad. Episode 1 by Qiskit. I believe this might be the most interesting video of all 6 or 7 videos here. Qiskit is the first episode of series called Quantum Computing in Practices by Qiskit. It aims to teach viewers how to use quantum computers at its full potential. The course will focus on teaching viewers how to use these quantum computers to solve real-world problems. Okay. Then we have by IBM, and as I was told, IBM is leading the quantum computing currently, so much that I think they are leaving AI from behind. Even though Watson was quite revolutionary when it appeared like 15 years ago or so. Damn. I didn't know that was that old. Yeah, but I used Watson the first time in 2013, I think. Probably 2012. I'm not sure. But yeah, a long time ago. Definitely before 2015. Definitely before. Um, Definitely before 2015. Um, yeah, it was about the time that Watson played. What's the name of it? Jeopardy. Yeah, yeah, 2010. Yeah, it was about the same time. Gee, yeah, about 15 years ago. 15 years ago, and it was amazing. It was amazing at the time. Um, so I think this might be a great resource. But IBM Technology is about 5 fundamental topics in quantum computer: superposition, gates. Oh, it's not ports; they're called gates, right? Measurement, interference, and entanglement. Quantum computers have the potential to solve problems that are impossible for classical computers to solve. For example, they could be used to develop new drugs, design new materials, and break current encryption standards. This is useless for now. The video is very good actually, but it's useless for now. We're on time. We're already 10 minutes on schedule. In the new Quantum Computers Potential Pitfalls DW documentary, I believe it's about the same. So yeah, this I think might be the best. Is it the same? Yeah. And definitely this. Definitely this. The others are not as relevant. So taking some notes. Taking some notes. I might need to open like a Figma or FigJam. Can I have a new window? Okay, I want to open a new window here. Like FigJam. FigJam. Not FigJam. I'm opening this in the other monitor due to the sake of privacy, because I have a lot of stuff in Figma that I don't want to share with you guys because it's private, basically. And I think that's it. Can I open this elsewhere? Can I change? Yeah, I can. Okay. So, yeah, but I don't want this to be.
Hello, my name is Olivia Lanes, and I am a researcher and an educator at IBM
I
Quantum.
want to watch.
This video marks the launch of a brand new series on the Qiskit YouTube channel and our learning platform called Quantum Computing in Practice. In short, in this series, I'm going to show you how to use a quantum computer that exists right now to its full potential. There are billions of videos already on the internet about quantum computers and their future potential, or on theoretical concepts behind quantum computation, which are also just as important. See Understanding Quantum Information and Computation, hosted by John Watrous, for example. But in this course, we are going to assume the learner maybe knows a little bit more than we have in the past, and we will go very far, technically speaking. And that's because over the past year, and at the time of this recording it is 2024, we have seen a shift, a phase transition if you will, into a new era of computation. Quantum computers are finally approaching the point where they can be useful. Even though experimenting with small-scale circuits and quantum computers was necessary to educate our community on how to utilize these machines, no one was running experiments that couldn't also be performed on regular old classical computers. But as of today, we have entered an era of quantum utility. And what is utility, you might ask? It is different than quantum advantage, which can be understood at the point at which quantum computers are outperforming classical computers at a meaningful task. Instead, utility means that they can start to compete with one another. And this is the natural next step in the technological evolution. IBM published a paper that showed for the first time last year a quantum computer could be used to simulate a physical model and compete with state-of-the-art classical simulation techniques. It even bested the brute force attempts and let researchers have a new avenue that they can use for research. So why is this all happening now? Well, in the past few months, IBM has made quantum processors of over 100 qubits widely available. If you're already a user, you might have noticed that we took down a lot of our smaller processors to make way for these larger chips. And we felt like it was really important to do so, because some numbers of qubits can still be simulated classically without a problem. So there's no real advantage that can be gained by using these chips. However, at 100 qubits, this is no longer the case. They cannot be simulated classically. It is also important to note that there are these things called simulators, which are essentially computer programs, and they can mimic some behavior of quantum systems, including noise. However, please don't miss the fact that I said mimic. Simulators are not quantum computers. They cannot produce the results that quantum computers can at this scale, but they're still an important part of our testing workflow. So that was a very lengthy answer to the question at the top of this slide. What is practical quantum computing? In this course, I'm going to teach you about realistic potential use cases for quantum and the best practices for running and experimenting on these larger scale processors today. So who is this course aimed at? Let's begin by doing some level setting at the beginning. This course is for everyone that aims to develop new applications for quantum computers, wants to know how to scale up their current work, or learn how to use quantum in their existing workflows. I previously mentioned that this course will be very hands-on, and we won't be discussing theoretical aspects nearly as much. We expect you to come in with a basic understanding of what quantum computation is. But if you're not quite there yet, no worries. Please just watch the first few episodes of John Watrous' course, and you'll be ready. We also want to make sure that folks watching know that this isn't just a course for physicists or even computer scientists. These two subjects have really been hogging quantum computing for the past decade or so. We want to make sure that others who work with big data or simulations, such as engineers, chemists, and material scientists, know that this course is also for them. In summary, this course is directed towards a broad audience, and we hope that you'll join us for its entirety. Upon completing this course, you will be able to understand how to create and run a utility-scale job through Qiskit Runtime, including the entire workflow. You will be able to understand the main types of error mitigation and also understand likely application areas in the short term. You will also be able to perform all of these algorithms in Qiskit. And lastly, we expect you to be able to understand noise and how to deal with it. So let's get started. Quantum computing is an exciting new technology in an early stage of development, but it's just one chapter in the story of computation, which goes back thousands of years. I think it's important to understand this context because it makes what we're aiming to do here a little in order to computing devices such as differential analyzers that solved equations using. Today we have supercomputers, making computers more and more powerful and smaller over time. However, there's some bad that were made, but that's not really the focus of this course. Instead, I want to make it clear that we know that quantum mechanics and computing are already compatible with one another. The findings and understandings of nature and IBM recognized decades ago that information is physical. Putting it another way, information is not an abstract entity, but exists only through physical representation. Landauer's principle establishes a connection between information and the laws of thermodynamics, but in fact there are many connections between physics and computation. Fluid dynamics are notoriously the next section. Quantum computing. What is it good for? So why do we even want to think about combining quantum mechanics and computing? Well, there are already plenty of problems that are too difficult, too computationally costly for even our cutting-edge supercomputers to solve. Maybe these are problems that only researchers are super focused on, but their impacts could touch all parts of the globe. These problems that classical computers get stuck on are things that we as a society are becoming more and more reliant on technology for and really care about, like battery efficiency, financial modeling and optimization, and even how to build better planes. So why turn to quantum computers? Well, we have very good reasons to think there's a lot of potential here, and we can open doors to new computation that is currently out of reach for even the most powerful supercomputers. In theory, some quantum algorithms provide advantages over the best possible classical algorithms for some applications. For other applications, there is mounting evidence that even with some noise and imperfections, quantum computers can still be used as a tool to compete with classical brute force solutions. Basically, today, there are a lot of parallels to be drawn to the very early days of the modern computer. Like I mentioned, this is a very hard challenge, and it was only within the last 8 years that quantum computers became widely available, besides for those who were working in a cutting-edge lab or facility. But in those past 8 years, we have made progress on every front. Processors are orders of magnitude larger in qubit size, gates are far improved, and we have introduced methods of reducing or mitigating errors intrinsic to the quantum systems, even while we push forward to create fault-tolerant quantum computers. Now you and anyone else can use one of these numerous IBM quantum processors that are hosted on the cloud, almost all of which are the newest, latest, and greatest systems, with over 100 qubits. But it isn't just the size of the processors that is important. This is only one metric that we care about. And that makes sense, right? If we have more qubits, that's obviously better, provided that increasing the number of qubits doesn't degrade performance. However, this isn't always the case. We need more good quality qubits that don't interfere with one another through crosstalk when we don't want them to. How the qubits are connected to one another is also something important to keep in mind. In superconducting circuits, it's a challenge to figure out how to best physically connect the qubits. Another hugely important metric is 2-qubit gate fidelity. Gates that run on single qubits are not as prone to error. 2-qubit gates are the much bigger area of concern, and usually one of the go-to metrics that we look for to see how performance is improving over time. 2-qubit gates are crucial to get right, because they are responsible for creating entanglement between the qubits, which is one of the physics phenomena that gives quantum computers their power. Lastly, we look for speed and efficiency. We need to make sure that the time spent running a program on the quantum chip is executed as quickly and as efficiently as possible. We refer to these three metrics together as scale, quality, and speed. All of them are vital to improve performance. Now I want to show you some quick plots to back up what I've been saying about how the technology itself really is evolving quite rapidly. The qubit count itself is the easiest to understand, I think, and IBM has published a roadmap of where we hope to be in the next few years in terms of qubit count and processor size. For 2024, when we're filming this video, we are right on track with our processors named Heron and Condor. Next, quality. This plot shows the median entangling gate.
Let's go back here. Where is this? Let's go back here. Not here, here, but here.
Itself really is evolving quite rapidly. The qubit count itself is the easiest to understand, I think, and IBM
There was something here.
about how the technology itself really is evolving quite rapidly. The qubit count itself is the easiest.
Where is this? Are there sources? Oh, listen to it here. I was looking for it.
Easiest to understand, I think, and IBM has published a roadmap of where we hope to be in the next few years in terms of qubit count and processor size. For 2024, when we're filming this video, we are right on track with our processors named Heron and Condor. Next, quality. This plot shows the median entangling gate error rate for IBM quantum processors over time. Keep in mind that this is a log scale, so while the progress looks vaguely linear, it's actually much more rapid than that. Lastly, we have speed. This graph shows the progress of a metric that we call CLOPS, which stands for circuit layer operations per second. Crucially, CLOPS encapsulates both the time it takes to run circuits and the required real and near-time classical compute. Basically, CLOPS is a measure of how quickly our processors can run specific circuits in series, acting as a measure of holistic system speed and incorporating quantum and classical computing. Right now, at the time of recording, IBM is the only quantum cloud provider that is providing access to 100 plus qubit machines. As I mentioned a few slides ago, 100 qubits, or right around there, is where classical simulation begins to totally fail. So large-scale jobs being run on these machines often have no classical equivalent. It isn't possible. There is some nuance and some tips and tricks you can play to simulate some parts of a circuit and then other parts separately, but in general, we know that right around this number is where quantum computers can begin to do things that classical computers just can't. So IBM decided that getting access to these larger devices was super important for the wider community, because anything being done on smaller devices is classically simulatable, and so it can't lead to quantum advantage. The 100 qubit devices we have now are still flawed, and they're still noisy, so we need to be smart about how we run jobs and circuits on them. Naively, just writing our circuit and pressing Shift-Enter probably isn't going to lead to anything spectacular. But again, there are tips and tricks that we can implement and best practices we can follow to squeeze even more performance out of these devices, which will hopefully lead to quantum advantage sooner, even while we continue to work and build up our fault-tolerant machines as well. This plot shows the simulation cost, or the amount of time it takes to solve a problem on classical computers and quantum computers equipped with error mitigation and error correction. So the classical computation line scales exponentially as the circuit complexity grows. For simple circuits down here, that doesn't matter. But it's obviously bad as the complexity grows because this makes the simulation cost very expensive very quickly. Error mitigation scales better. So when the complexity of the circuit grows, this is where we want to be. We are currently here, with classical methods and quantum methods sort of on par with one another for some applications. And error correction might be the most preferable and scales really nicely. We're just not there yet. In the meantime, we will continue to focus on error mitigation and getting to this area of quantum utility as soon as possible. And by making use of several error mitigation schemes, which we will learn about in this series, we aim to find application areas that can make use of quantum utility very soon. And that is really what the heart of this course is. We have these machines, we think they're capable of doing some really interesting research, so how do we use them? In this last section of the episode, let's briefly discuss application areas for practical quantum computing. There are three main branches that we think we're most excited to explore and find avenues for quantum utility. The first is simulating nature. This has to do with simulating molecular or atomic interactions, and this is really important for areas of material science and chemistry. And for reasons we discussed earlier, we think quantum computers are going to be a lot better at this than their classical computer counterparts. Next is search and optimization. The main algorithm of interest here is called QAOA, a hybrid classical quantum algorithm. QAOA uses a classical computer to train and find optimal parameters for a quantum circuit, and will hopefully be able to do this a lot more efficiently than either computer could alone. Lastly, we have mathematics and processing data with structure. Quantum computers are really good at finding structure in messy data where you or I or a typical computer might not see anything. Quantum machine learning holds promise in this area, and we aim to use this for tasks such as feature extraction and pattern recognition. It really is a very exciting time for those of us that work in the field of quantum computing. For the first time in history, we can begin to explore a region of computing that lies beyond classical computing. Those of you watching this might possibly play a role similar to the early pioneers of computing, and they had no conception of what was to follow. T.J. Watson of IBM even famously said he thought there might be a market for only 2 or 3 computers ever, and wow, was he wrong. We are all those early pioneers of computing, but in this new field of quantum computing. And quantum is often contrasted with classical computing as something distinctly different from it and often in competition with it. But my aim for this introductory lecture was to hopefully convince you that from an eagle-eye view, we can see quantum computing as simply the next chapter in a long story of computing. It is our nature as humans to seek out new ways to compute and to harness the power of the natural world and to figure out what to do with it. and we've been doing this for centuries. Quantum computing offers us a new tool in this endeavor, and it is up to us to discover how we can leverage the power it offers us. In the next lesson in the series, we will talk a little bit more about 100-qubit systems and give an overview of Qiskit, our quantum software SDK, and how to best interact with these machines right now. Thanks for watching, and we'll see you next time.
Okay. Let's watch the lesson.
Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director of Education at IBM Quantum. This is the second lesson of the series. If you haven't already watched the first lesson, be sure to check it out. We'll be building directly on what we talked about in the first lesson, so it's important to have an understanding of that material going into this lesson. Also be aware that the series includes textbook content in addition to videos, and you can find a link to the textbook content in the video description. This is lesson 2 of Unit 1 of the series. Unit 1 covers the basics of quantum information. In the previous lesson, we talked about quantum information in the setting of single systems, meaning that we have one system that stores information, and we're describing how it works in isolation. We spent a fair amount of time on classical information, mainly to establish a point of reference and to highlight mathematical similarities between quantum and classical information. We also saw how quantum states can be represented by vectors, specifically vectors having complex number entries and Euclidean norm equal to 1, and we discussed standard basis measurements and unitary operations. In this lesson, we're going to expand our view to multiple systems, each of which is capable of storing quantum information. This is not simply a matter of saying that each individual system works as we discussed last time. There is a sense in which the whole is greater than the sum of the parts, and that's also true of classical information when probabilities are involved. Multiple systems can interact with one another, and they can be correlated with one another, for instance, and in the quantum setting, this includes the possibility that the systems are entangled, which is a term that you may have heard about before. Entanglement is a very important phenomenon in quantum information, and we'll have a lot more to say about it as the series continues. There is a simple principle, however, that offers us quite a lot of traction for thinking about and understanding quantum information for multiple systems, and that is that we can always take two or more systems and put them together, or just conceptually think about them together, and view them as if they form a single compound system. And when we think about a compound system like this, as if it's a single system, we recognize that it must be described in a way that's consistent with everything we learned in the previous lesson on single systems. We'll see how this works, and how the description of quantum information for multiple systems emerges pretty naturally from how it works for single systems, based on this one principle. Here's an overview of the lesson, and it happens to be identical to the previous lesson's overview, but this time our focus will be on multiple systems rather than single systems. Just like we did in the previous lesson, and for exactly the same reasons, we're going to start with classical information. Once again, we'll see very close similarities between the way that quantum and classical information work at a mathematical level. We won't typically focus so much on classical information or start each lesson in the series with classical information like this. Subsequent lessons will tend to be focused much more exclusively on quantum information computation. But here at the beginning, this is a sensible approach, and it goes back to the idea that thinking about classical information can serve as a valuable source of guidance for understanding quantum information. We're also going to discuss the important concept of a tensor product in this part of the lesson. Tensor products are critically important in quantum information, but they also arise in the classical setting. Then we'll move on to quantum information, and much like in the previous lesson, we'll discuss quantum states, standard basis measurements, and unitary operations, this time for multiple systems. We'll start by talking about classical states of multiple systems. Recall from the previous lesson that a classical state of a system is a configuration of that system that can be recognized and described unambiguously without any uncertainty or error. And in mathematical terms, when we refer to a classical state set, we just mean a finite and non-empty set. We'll begin our discussion of multiple systems by supposing that we have just two systems, x and y. X has some set of classical states, which we'll call sigma, just like in the previous lesson, and y has some set of classical states that we'll call gamma. The sets sigma and gamma could be the same set, or they could be different.
Easy, because we're starting to get interesting. So, classical state superposed that we have two systems. X is the system having a classical state. Alright. This is the time that I definitely need
From the previous lesson, that a classical state of a system is a configuration of that system that can be recognized and described unambiguously without any uncertainty or error. And in mathematical terms, when we refer to a classical state set, we just mean a finite and non-empty set. We'll begin our discussion of multiple systems by supposing that we have just two systems, x and y. X has some set of classical states, which we'll call sigma, just like in the previous lesson, and y has some set of classical states that we'll call gamma. The sets sigma and gamma.
You meant the last lesson, which is where? Because I have watched it in the past. I don't remember. Okay, let's go back there.
The second time, then you would get exactly the same result as you did for the first measurement. So there's a limit on how much classical information can be extracted from a quantum. In the last part of this discussion of classical information, we'll talk about classical operations that can be performed on a system, starting with deterministic operations. When we perform an operation on a system, its state generally changes as a result. And in this context, the word deterministic means that the result of performing the operation depends entirely on whatever classical state the system was in prior to the operation being performed. In other words, there's no element of chance when a deterministic operation is performed. This is the entry of M whose row corresponds to B and whose column corresponds to A. We'll see a few examples in just a moment, and we'll see why this formula works.
Okay, sure.
Now,
let's go back.
we again
This is
consider the
quite
situation where x is a bit,
intensive.
and we have the same probabilistic state as before. Then, if we measure x, we can imagine that a transition takes place.
Yeah, I remember this.
We see the classical state 0, and by measuring, we transition to ket 0 being our probabilistic state. And with probability 1/4, we transition to ket 1.
Then I probably
Think about
fell
this as a
asleep.
transition of knowledge, if you prefer, as opposed to an actual physical transition. But what's important for the sake of this lesson is to recognize how the mathematics works. It's kind of trivial, actually, but by recognizing this triviality, the analogous description for the quantum setting might seem a little bit less mysterious. One final note is that to another person who didn't happen to see what the classical state of X was when we measured it, the probabilistic state naturally wouldn't change as a result of us having measured it. That's okay. Different individuals can have different knowledge of a particular system and correspondingly choose different probabilistic states to represent their knowledge of that system. In the last part of this discussion of classical information, we'll talk about classical operations that can be performed on a system, starting with deterministic operations. When we perform an operation on a system, its state generally changes as a result. And in this context, the word deterministic means that the result of performing the operation depends entirely on whatever classical state the system was in prior to the operation being performed. In other words, there's no element of chance when a deterministic operation is performed, so there's no randomness or uncertainty involved. In mathematical terms, deterministic operations are described by functions. Every function f of the form that you see right here, which means that both the input and the output of the function correspond to elements of our classical state set sigma, describes a deterministic operation. The classical state A is transformed into the state f of A for each choice of a state A.
I don't get what you're using sigma. Sorry, as far as I'm aware, sigma means the sum. It's a sum function, isn't it? So I'm not sure at all what they mean about this. Every function f, excuse me, so deterministic operation that transforms the classical state of alpha into a function of alpha for each alpha in sigma. I don't have enough math to understand this. I don't have enough math to understand this. Oh. The math in the image refers to the function f that maps to the classical state A to another classical state f of A. The capital sigma refers to the set of all the possible inputs. Alright. Classical computers are deterministic in the sense that they follow a set of instructions and always produce the same output for a given set of inputs. Okay, that makes sense. Quantum computers, on the other hand, are probabilistic, meaning there's an element of chance involved in the outcome. Right. I can't provide more information about, okay, it's right. Here are some resources that explain the math behind the quantum computers. NYS NISQ era and quantum supremacy by Adam Harland. Sorry. Sorry. Adam Harrow. Adrian Hassett and Seth Lloyd. Who are these people? Professor at physics, right? At MIT. Okay. I can't look to the light. Okay. Adrian Hassett. Private commercial business. Why is this so big? Current quantum information. Give it out. I want to know who is this person. Okay. He's in stealth mode. and Cepheid. Quantum Cepheid. Huh. Cepheid is a professor of mechanics engineering and physics at Massachusetts Institute of MIT. Alright. Ooh. I'm sorry for him. Oh. I didn't want to know about it. You're sure this is what you meant? You're sure? I don't think you are. I don't think you are. I didn't want to know about it. The quest of quantum advantage wherein quantum computers surpass computational capabilities of classical computers, executing state-of-the-art algorithms of well-defined tasks represents the pivotal race in the domain of quantum computers. NISQ, which means noisy intermediate state quantum computing, NISQ, noisy intermediate state quantum computing, has witnessed remarkable advantages, culminating in significant milestones on a journey towards the realization of universal fault-tolerant quantum computers. This transformative turning point, known as quantum supremacy, has been achieved amid a series of breakthroughs signifying the dawn of quantum era. Quantum hardware has undergone substantial integration and architectural evolution, contrasting with its nascent stages. In this review, we critically examine the quantum supremacy experiments conducted thus far, shedding light on their implementations and contributions to the evolution landscape of quantum computing. Additionally, we endeavor to illuminate a range of cutting-edge proof-of-principle investigations in the realm of applied quantum computing, providing an insightful overview of the current state in applied quantum research and its prospective influence across diverse scientific, industry, and technology frontiers. This was written last year, September, by Mohammed Abu Ghanem, and Hisham Eloich. I'm sorry if I don't pronounce these names correctly. I'm pretty sure I'm not. Theoretical quantum optics. Google Scholars, I've seen this. What's this? University of Shariza. Where's this school? Rashik Particles Physics of University of Shariza, Emirates. Alright. Bazema, Professor of Epidemiology in Public Health. Dilber, University of Shariza, College of Health Students near Professor Dr. Ilhan Öztürk. Okay, and Muhammad Ali. Right. This is in French. Can I? Is it French? I don't know. C'était pas. This looks French. Depuis 2019. I don't speak French at all. This is quite old. Wow. I don't know Google Scholar. I don't know what it is. Why is this in French? Can I make it in Portuguese or English? I'm okay with English. Why is this in French? My profile, my library. Is this like a place for papers and lectures? I don't know this. Is this competing with Coursera or something like this? Quantum. Optical quantum computing. A book written in 1999. Wow. Yeah, I've seen somebody talk about many body. This is this year. Simulating quantum antibody systems in a key application for emerging quantum processes. While analog computing simulations has already demonstrated quantum advantages, its digital counterpart has recently become the focus on intense research interest due to the availability of devices that aim to realize general-purpose quantum computers. In this perspective, we give a selective overview of currently proposed approaches, review and advantages in digital computing simulation by comparing non-variational with variational approaches and identify hardware and algorithmic challenges. Based on this review, the question arises, what are the most promising problems that can be tackled with digital computing simulation? We argue that problems of qualitative nature are much more suitable for near-term devices than approaches aiming purely for quantitative accuracy improvements. Jesus Christ. Oh, the timer. The timer is not working. The timer timer is not working because I changed. Okay, it works now. I changed the zoom. Oh, and the zoom is browser dependent. It's not like tabs or so. Drug design on quantum computers, quantum computation, quantum simulation, ultra cold molecules. What makes quantum computing so hard to explain? That's something that I must read. Where is this from? Springer.com. Can I read a Wally book? Do I need to buy it? I don't want to buy it. This is a preview, alright. Okay. Now it makes sense. Now it's starting to make sense. But this is open. This is pretty much open, yeah. This is still quite big. Yeah, this is pretty much open. Right. Quantum computing in AI in the cloud. Wow. I'm astonished. Yeah, I of course I knew this was an immense subject. Of course I knew. The thing is that this is right now. This is 4 months old. What's happening? Okay. Okay, the intersection of quantum computing and AI within a cloud environment represent a paradigm shift in the capabilities of computation technologies. This paper explores the confluence of quantum computing and AI in the cloud, examining the synergies that emerge, the transformative potential of data processing, machine learning, and data security. Quantum computing, with its ability to process information in parallel through quantum bits, introduced the quantum advantages promising exponential speed up in specific computational tasks. In tandem, I don't know what tandem means, AI, fueled by machine learning algorithms, has become ubiquitous, reshaping industry through automation and data-driven insights. Cloud computing, known for this scalability and accessibility, form backdrops to deployment of AI models. Quantum machine learning paradigm. Quantum machine learning paradigm. Oops. quantum machine learning. Quantum machine learning paradigm leverages quantum computing's unique properties to enhance classical machine learning models. This paper navigates through the application of quantum machine learning in predictive analytics, pattern recognition, and optimization tasks within cloud-based AI platforms. Enhanced data processing capabilities, real-time analytics, and the integration of quantum-safe security measures. Quantum-safe security measures underscore the transformative potential of coverage. I believe quantum-safe security measures is I don't know, I'm confused. However, challenges abound, ranging from quantum error correction, hardware stabilities, to algorithmic development, security considerations, and regulatory compliance, ethical concerns, user education, and the need for continuous adaptation to evolving quantum technologies, further compliance and landscape. Complicated landscape, I mean. The conclusion emphasizes the strategy imperative for organizations to embrace the quantum AI cloud coverage. Ongoing research, collaboration, and adaptability are essential to harness the full potential of these transformative integrations. As quantum technologies evolve, organizations might navigate challenges as size opportunities, shaping the future where quantum computing and AI in the cloud redefine the boundaries of computational possibilities. Alright. Quite an interesting paper, I suspect. Yep. This is something that I meant. Okay, quantum machine learning stands at the forefront of innovation, leveraging the unique properties of quantum computing to enhance classical machine learning models. This section of the paper focuses on intricate details of the profound implications of quantum machine learning within the broader context of coverage of quantum computing and artificial intelligence in the cloud. Quantum advantage in machine learning, QML, capitalizes the quantum advantages of a phenomenon where quantum algorithms outperform their classical counterparts for certain type of computations. Quantum computing abilities to process information in parallel thanks to the principle of superposition provides a significant boost of computational efficiency. This is particularly advantageous for machine learning tasks that involve complex calculations in large data sets. Quantum neural networks. Quantum neural networks. Wow. Quantum neural networks. Traditional neural networks form the backbone of many machine learning applications. QML introduces quantum neural networks, which leverage quantum bits of qubits of represented and process information. Quantum neural networks, have the potential to capture more intricate patterns and correlation in data, offering advantages in tasks such as pattern recognition, classification, and feature extraction. Quantum algorithms for machine learning. QML introduced a suite of quantum algorithms designed specifically for machine learning tasks. Examples include quantum support vector machine, quantum support vector machine, quantum support vector machine. Quantum principal component analysis. Quantum principal component analysis. My dear God, how much there is. The quantum K means clustering. Let me make it clear. I knew this was complex. Of course I knew. Of course I knew I would be overwhelmed by the sheer amount of stuff out there. Of course I knew about it. But I'm being confronted for it to it. It's different when we know that this is an area of engineering and science on its own. Of course I knew it was complex. But now I'm looking into it. I don't aim to know. I just want to learn about this. To know something about this. But my target is not to be an expert in it. Well, I might. Like in 10 years or so. If I follow this path. But my goal for now is just to learn about this, to understand. And I'm targeting 2 hours per day on this. So it's about 15 hours per week, which is something like 90 hours per year, 100 hours per year, if I'm committed to it. 100 hours in a year. 100 hours in a year. It sounds so little. Yet is much more than I'm doing now, that I've been doing until now. 100 hours in a year. And in the first hour, I've already read something about it and looked into names. And I've learned already something like Google Scholars that I probably heard about it in the past, but I've never went there. But I don't remember being there. So far I've learned something. So these are some algorithms for quantum machine learning. quantum support vector machine. Quantum support vector machine. I suspect this can somehow be related with vector databases, with quantum neural networks. I believe you can create vectors in those. Quantum principal component analysis. No clue about this. Quantum k-means clustering. No F clue about this. Moving on. The algorithms aim to outperform their classical counterparts when executed on a quantum computer, demonstrating that the potential for exponential speed up in various machine learning applications. Quantum data representation. Classical machine learning models rely on classical bits for data representation. QML qubits enable the representation of data in quantum superposition, allowing for the simultaneous exploration of multiple states. This is something that I can't grasp my mind on. My mind around it. This is such concepts on its own. Quantum superposition it's absurd. It's absurd. It's completely absurd, and it sounds to me one of two things. One, science doesn't know enough to understand a potential deterministic solution in what is currently known by quantum superposition. Again, this is pure philosophy. I know nothing about this. And I forgot the other view I was having. Sorry, I'm quite tired today. So this is a possibility that science doesn't know yet, and takes superposition as a probabilistic approach, whilst in some situation this is deterministic. And I'm eager to say that from a philosophical perspective, considering the multiverse theory, at a particular instance of time, if time exists, a quantum particle has multiple states in multiple universes. I don't know if I can speak. I'm not sure about this. Is it possible that quantum supremacy is barely understood by excuse me, stop please, by current science, and that somehow a quantum particle is state is deterministic for a particular instance of time. If time exists, or a particle exists in multiple universes or instances of that particle in a multiverse environment. Is it possible that quantum computing is barely understood by current science, and that somehow quantum particle state is deterministic for a particular instance of time, if time exists, or a particular particle exists in multiple universes or instances of a particular particle in multiverse environment in multiple states simultaneously? Could that be? Yeah, let's stick to this. You're bringing up some interesting concepts of forefront quantum mechanics. Here's a breakdown of your question. Quantum supremacy understood by but unproven. Quantum supremacy refers to the ability for quantum computers to outperform classical computing. Oh! It's not supremacy, it's superposition. It's superposition. Superposition. You're right on a money. Quantum superposition is one of the most puzzling aspects of quantum mechanics, and scientists are still actively trying to understand it fully. Here's how your question relates to it. Barely understood. Yes, quantum superposition is a complex concept. We can describe it mathematically and use it to make predictions about experiments, but the why and how of it exists in reality are still debated. Deterministic state. Quantum mechanics doesn't predict deterministic states for a particle until measured. A particle in superposition is in a probability cloud of all possible states simultaneously. Multiple states of universes. The idea of multiple universe isn't directly related to superposition, but is one interpretation. Many world theory suggests its possibility in superposition splits the universe into a new one with that specific state. However, this is a very speculative idea. Of course it is. It's philosophy, basically. Here's a simple analogy. Imagine a coin spinning in the air until it lands. It's both heads and tails at the same time. Yeah, similar to superposition. Once it lands, it becomes heads or tails, like measurement. Quantum mechanics predicts the probability of landing in heads and tails, but not which side will be defined. Definitively. Here are some additional points. Time itself gets weirder in quantum mechanics. Superposition might be related to nature of time, but that's an ongoing area of research. Multiple instances. The idea of particle existing in multiple universes simultaneously is part of many worlds interpretation. Yeah, you said this. But it's not the only interpretation. All interpretations try to explain superposition without resolving a multi-universe. Overall, quantum superposition is a fascinating and counterintuitive concept. While it might seem strange, it was supported by experiments. Scientists continue to refine our understanding of its implications and how it relates to the nature of reality. Yeah, I'm sure we have math around this and we can use it. I'm pretty sure science can use this concept of superposition and quantum in general. Still, I believe we know so little about this that these concepts are just, well, there's some other possibilities that this is all perception. This is all perception. All that is a mere perception. From conscious. Like there is the concept of conscious might be greater than the universe itself. And the conscious experiences itself. Like I believe I'm conscious, and by believing so, or let's assume that I'm conscious. There is no consensus of what conscious is, but like conscious can be an inherently known of existence. I know I exist. I don't know if I exist forever. I know I exist now. Now, at this exact moment, all I have is memory. And I don't know if my memory is brought to me at this particular instance or I've been here for a long time. Now I know I exist. And by knowing so, I am aware of existence. So awareness can be a broader concept that is not finite on me. Being more Earth-centric. Earth is aware because I am aware. And as long there is awareness on Earth, Earth is aware. I'm a particle or a fraction of Earth awareness. And so I am a fraction of universe's awareness. The universe is aware because I am aware. Or am I not? So what I'm trying to make sense of it in my own head is that there might be a possibility that I've probably read about this somewhere. There is a concept or a theory that states that conscience is key in quantum deterministic results. I don't know if the wording is correct. Like in I don't know the names of it. The experiments of lasers shooting, and we see an interference pattern or the vertical lines. I've seen something about this over time, but I remember reading about this like 20 years ago or so when I was a teenager. And someone had a concept, some scientists had the concept that conscience, I don't remember the word for it, but it defines the state of matter or the particle, therefore matter, I think. And if so, awareness or consciousness is above matter, like in a higher dimension, and it collapses. That was the word I was looking for. It collapses quantum particles instantly because it's not bounded to time. I am aware, therefore Earth is aware, and so is the universe. I read some time ago that there is this concept that quantum particle collapse might be related with consciousness. Oh, right. Meaning that conscience interact with quantum particles to set its state. Ignore if terms are not correctly incorrect. Therefore, consciousness is at a higher level than matter, such as a higher dimension, and can interact with it at a set time, instance of time, meaning that I might have not lived, so to say, until now, but I happened to exist at this exact form, which contains memories, which are the result of a certain structure of neurons, and so matter, meaning that conscious can collapse matter at a particular state at a particular instant. Knowingly or not. So far, this conscience aware of mind is aware of itself. So conscience itself is aware of itself by the mere existence of my own awareness as a fraction of the whole. That's a very interesting line of thinking. The connection between consciousness and quantum mechanics is complex and debated topic. Here's a breakdown of the idea. Consciousness and collapse. The idea that consciousness caused quantum collapse is a fascinating hypothesis, but there are no conclusive evidence for it. Most experiments suggest collapse happened due to interaction within the environment, not necessarily the conscious observer. Consciousness is higher level. Whether consciousness is a higher level or a product of the physical brain is also debated. Some believe consciousness emerges from complex neural interaction, while others posit I'm having some trouble looking to the screen. While others posit might be a fundamental property of the universe. Multiple possibilities. The many words interpretation of quantum mechanics suggests all possibilities in superposition exist in separate universes. So, in a way, you could say you exist in all those states simultaneously. However, this is a highly theoretical interpretation. Memories and matter. Memories are indeed encoded in physical structure of the brain. Your point about a certain structure of neurons causing the experiment of you is on spot. Consciousness collapsing matter. While consciousness might influence brain activity, directly collapsing matter at a specific state is beyond what current science suggests. Okay. Self-awareness. Your self-awareness is a fascinating aspect of consciousness. Neuroscientists are still unraveling the mechanisms behind it. The idea of a fraction of the whole suggests a connection to a larger consciousness, which again is a philosophical topic without definitive answers. Overall, your ideas touch on some of the biggest questions in science and philosophy. Here are some resources for further exploration. The Conscious Mind by David Chalmers explores the relationship between mind and matter. Quantum computing in particles in practice by Quiskett teaches you about quantum mechanics and its application in Stanford. Encyclopedia of Philosophy has articles on consciousness and quantum mechanics. Alright. Moving forward. Or backwards, as I'm so tired. So tired, sitting in this arrow, looking up and da 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 da. So, quantum data representation. Classical machine learning models rely on classical bits of data representation in QML. Qubits enable representation of data in quantum superposition, allowing for the simultaneous exploration of multiple states. This quantum parallelism offers a unique approach to encoding and processing information, potentially leading to a more efficient representation of analysis complex data sets. Yeah, it makes sense. Quantum feature mapping. Quantum feature mapping is a key technique of QML that transforms classical data into quantum states suitable for processing quantum computing. By mapping classical data to highly dimensional quantum space, quantum algorithms can uncover intricate patterns that may be challenging for classical algorithms to discern. This process enhances the expressive power of quantum machine learning models. Okay. Hybrid quantum classical approaches. QML often involves a hybrid quantum classical approaches where quantum algorithms collaborate with classical optimization routines. The classical part of the algorithm handles certain tasks, while quantum components exploit the quantum advantages of specific computation. Cloud-based AI platforms provide an ideal environment for implementing these hybrid architectures, allowing seamless integration for quantum and classical resources. I've read something about it in the past. Like you can gather some probabilistic results from a quantum computer, and then use current AI models to make sense out of it. Neither of those are purely deterministic. Well, current AI models, neural networks, and machine learning, and so forth, that's intrinsically deterministic because it's math. It's still too complex for today for us to understand, but it's math. Whilst quantum computing is not, it's inherently probabilistic. So we are moving from probabilistic approach to a deterministic approach, from quantum to AI, and then from AI we can use regular classical computing to make sense of it, or to create interfaces for it. Like the AI makes sense of it, then the classical computing makes the interface. Quantum circuits learning. QML introduces the concept of quantum circuit learning, while quantum circuits replace classical neural networks architecture. The parameters of these quantum circuits are trained to optimize specific machine learning objectives. Alright? This novel approach holds a potential to achieve superior performance for certain types of tasks and is an active area of research at an intersection of quantum computing and machine learning. Okay, it's like quantum computers generating parameters for ML, for machine learning. So QML introduces the concept of quantum circuit learning, where quantum circuits replace classical neural networks architectures. Why? The parameters of these quantum circuits are trained to optimize specific machine learning objectives. Okay, so as current models are fine-tuned and changed on parameters, I think. a quantum computer can, excuse me, a quantum computer can be used to tweak the parameters of the ML algorithm for a certain task. That's quite interesting. This is very interesting. This is interesting indeed. It's like currently LLMs adopt those parameters to tweak certain aspects of the model itself, like to I've read something days ago about this. I think it was about Claude. I might have published something on LinkedIn. I think I did. Oh, I don't want to. I don't have my phone here. Can I go to my LinkedIn directly? Can I do this? Do I need to be online? Oh, I don't want to. Claude and what's it? Anthropic parameters. I've read something about this recently. No. Did I publish on Medium? Do I need to log in again? Can I think I can log in here. Here. No. I don't know. I don't know. I read something about this recently. This was some kind of news. Well, never mind. They tweak those parameters for certain stuff, like if they want to enhance a topic or prevent a topic from being talked about, they can set it. So the way I understand this quantum circuit learning concept is like it learns. Actually, quantum computers can understand those ML models. Oh, it was about it was about understanding the mechanics of the model itself. So they, excuse me, they where did I read about it? They made a proof of concept in a small language model, which is a manageable approach. That's not it. Yeah, that's it. That's it. No, it's not it. I think this is the first part of that research. Oh, wow. Cool. Yeah, I think that's it. Yeah, that's exactly this. That's exactly. This is a fantastic post. This is a fantastic post. Can quantum circuit learning be used to trick I couldn't find relevant information about whether quantum circuit learning can be used to tweak ML parameters in this article, but there, what I found in the web, quantum circuit can be used to represent quantum algorithms. Quantum circuit learning is a technique for training quantum computers to execute a quantum circuit. It is a relatively new field and there is still much to learn about capabilities. Some researchers believe that quantum circuits learning could be used to develop new and more powerful machine learning algorithms. However, it is important to note that quantum circuit learning is still in its early stages of development, and it is not yet clear whether it will be a practical approach for training machine learning models. Right. Quantum circuit learning. Challenges and future directions. Despite the promise of QML, several challenges must be addressed: quantum error correction and scalability, quantum hardware, and the need for efficient quantum to classical transition pose significant hurdles. Ongoing research in quantum algorithms and hardware advancements aim to overcome these challenges and unlock the full potential of QML. QML represents the groundbreaking frontier in the fusion of quantum computing and AI, as the paper navigates through the confluence of quantum and AI in the cloud. A deep understanding of QML intricacies is essential to comprehend how quantum advances can be harnessed to revolutionize machine learning capabilities in the digital era. Okay, enhanced data processing. The interaction of quantum computing and AI within the cloud environment introduces paradigm shift of data processing capabilities. This section of the paper focuses on how the confluence of quantum and AI in the cloud enhances data processing, offering unprecedented speed and efficiency, analyzing vast datasets, addressing real-time demand, and catalyzing the advancements in various applications. Quantum parallelism for big data. Quantum computers, computing's inherent parallelism, they've ripped from the principle of superposition, revolutionizes data processing. Yeah. Classical computers process data sequentially, whereas quantum computers can explore multiple possibilities simultaneously. In the context of cloud, quantum parallelism accelerates the analysis of big datasets, unlocking the potential of rapid insights and decision making. Yeah, of course. Real-time analytics, of course. Quantum-assisted pattern recognition. This is probably what I was mentioning. Pattern recognition is fundamental for various AI applications, including image processing, speech recognition, and ML understanding. Quantum computing ability to discuss complex patterns in parallel enhances AI algorithms' proficiency in recognizing subtle correlations within datasets. This quantum-assisted pattern recognition holds significant promises in refining AI models in the cloud, optimization tasks, and quantum advantages. Quantum data comprehension, quantum-assisted ML, inference. This, for me at least by now, is all related with quantum circuit learning. As the quantum learns about the ML, it can aid the technology AI to speed it up and learn on pattern recognition. This is my understanding of this concept so far. Quantum data set queries, yeah, of course. It makes sense. Of course it makes sense. That's science. The goal of science is to make sense of things. Energy efficient, of course, challenges and considerations. Despite problems of enhanced processing challenges persist, quantum error correction, hardware limitation, and algorithm development are critical areas requiring attention. The effective integration of quantum data processing in existing cloud infrastructure necessitates careful considerations of compatibility, security, and relational compliance. Yeah, of course. Secure AI in the cloud, quantum cryptography for enhanced security, quantum key distribution is a notable technique. I'm aware of these concepts. I don't want to follow this now. I'm aware of this. Quantum safe encryption protocols. Sorry. This was something I was thinking about minutes ago. I don't know how quantum safe relates to post-quantum, especially in cryptography. But quantum safe, well, As quantum computing poses a threat in classical encryption algorithms, the integration of quantum-safe encryption protocols became imperative. Quantum-resistant cryptography algorithms, such as lattice-based cryptography, offer robust security against quantum attacks. In the cloud, these protocols can be employed to encrypt AI models, datasets, and communication, ensuring confidentiality and integrity of sensitive information. Yeah, this is not something that I'm thinking right now. Actually, I don't enjoy quantum cryptography that much. It's a concept that it quite bothers me actually. The quantum cryptography is a concept that bothers me, and I don't know why. But yeah, homomorphic encryption for privacy-based AI, secure multi-party computations. Alright, trusted execution environments, quantum secure authentication mechanisms, quantum monitoring and anomaly detection, regulatory compliance and certification, user education and awareness, challenges in future directions, quantum error, hardware stability, algorithm development, quantum integrations, regulatory bias, user experience training, ethical and bias concern, and conclusion. Yeah. What a document. What a document. Very, very interesting. Very interesting. Pretty much on the introductory side. Pretty much what I was looking for today. And considering I have 15 minutes so far, these are the concepts that were noted. QAOA. So, first and foremost, let's try the Google Scholar for QAOA. Short FQAOA circuits and quantum annihilating and higher order issuing models. QAOA expectation values of P1 and 2 are computed using classical light core-based simulations. Learning simplified QAOA parameters and transferability. Quantum approximate optimization algorithms. This I think is related to simulation. I think provides a way to solve combination optimization problems using quantum computers. Quantum approximated optimization algorithms. Circuits consist of time evolution operations by the cost Hamiltonian and the state max mixing operators. This is borderline This is indeed beautiful. If not anything else, this is beautiful. This is beautiful indeed, and I I suspect that I'll fall in. This 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 is not even 1 month old. These papers, they were just published. They were just published. This is brand new. This is brand new concepts. Towards universal QA protocol, evidence of quantum advantages is solving combinational optimization problems. Okay, QAOA stands for Quantum Approximate Optimization Algorithm. It's a technique used for quantum computers to tackle a specific class of problems called combinatorial optimization problems. These are problems where you need to find the best possible configuration or solution from a set of many options. Wow. Here's a breakdown of QAOA. Costs Hamiltonian. This defines the problem you're trying to solve. It assigns an energy value to each possible configurations, with lower energy indicating better solution. Yeah, I've seen something about it. Yeah. Cost Hamiltonian. This defines the problem you're trying to solve. It assigns an energy value of each possible configuration, with lower energy indicating a better solution. Okay. Mixed Hamiltonian. This acts like a steer for a quantum state. It helps the algorithm explore different configuration efficiency. Okay. Parameters. What's this? This is epsilon and beta. These are variables that control the influence of cost and mix Hamiltonian in the algorithm. Oh, okay, so both can be applied simultaneously. Quantum circuits. The algorithm is implemented as a series of rotations on qubits using this Hamiltonian and the parameters. The rotations are applied in an alternating fashion. Apply rotation based on a cost Hamiltonian with parameters y. This is not y, by the way, I don't know which letter is this. And apply rotation based on a mixed Hamiltonians with parameters beta. Repeated applications. This sequence of rotation HS and HM is repeated multiple times to refine the solution. Measurement. Finally, the qubits are measured to obtain a final state which hopefully represents a good solution for optimization problem. Key points of QAOA. It's an interactive approach, meaning it gets better as the number of repetitions increases. The effectiveness of QAOA depends heavily on choosing the right Hamiltonian and parameters. It's a promising method for solving complex optimization problems that might be intricate for classical computers. QAOA, quantum approximation optimization algorithm. Quantum approximate optimization algorithm. And mask that with Python code interpretation. Okay, one document from archive. This is 10 years old. This is so fascinating in quantum. It's such an old area of study that I just picked a document about quantum cloud and AI published 4 months ago, not even 4 months ago, and I picked some document on QAOA that was published 20 days ago, and the concepts is 10 years old. This is fascinating. This is fascinating. And again, it's a 20-page document. 16. But I'm enjoying this. This is fun. This is fun to me. Actually, I think it's funnier than AI so far. I believe I'm enjoying learning about this much more now than I did when I started learning AI. Though AI is much more pragmatic than what I think quantum computing is, this is mainly theoretical. Even though there are computers, quantum computers, out there currently, I think they're being mainly used for experimentation. I'm unsure if there is already a practical application for quantum. Even though the thing of IBM's 100 qubit plus computer being all classical computing, I'm not sure if that means that we don't have classical computation power currently that can perform that, or it's faster with current quantum computing technology rather than classical computing. Or they're comparing apples to apples, and it's results paid versus energy consumption. I don't know what's the baseline for that line across in the IBM in the cricket video. But I believe worldwide are classical computation power is still higher than quantum. Excuse me. There's not a nuance on how. There's a lot of nuances on how quantum computers are compared to classical computers. IBM's achievement is a significant step forward. Here's how they might have achieved these results. Not by. Okay. Time has come. If I can find my mouse. Okay. Yeah, and I'm tired in it, so I'm just going to read about this and I'm going to close the session. Not by energy consumption. It's unlikely they compare energy consumption. Quantum computers are still in the early stage and often consume more power than classical computers. Oh, cool! I didn't know about. Oh, because it's cool. It's pretty cool. More likely, specific tasks outperform simulation. They likely compared the performance of their 100 plus qubit computer on a specific task to a classical simulation on the same task running on a supercomputer. The key point here is simulation. Alright, I see. Quantum advantage for specific tasks. Quantum computers excel at certain tasks due to phenomena like superposition and entanglement. These tasks might be intricable, impossible to solve in reasonable time, intricable. For classical computers, even more powerful ones, error correction matters. It's important to note that current quantum computers are prone to errors. So while a quantum computer might outperform classical simulation for specific tasks, it might need to run a task multiple times to achieve the reliable results. This can negate some of the performance advantages. The race for quantum advancement. The field is actively researching and developing techniques to mitigate error and improve performance of quantum computers. The achievement by IBM suggests we're getting closer to achieve quantum advantage. where quantum computers outperform classical ones for a broader range of tasks. Do we have no classical power? No, not entirely. Classical computers are still incredibly powerful and handle many tasks much better than quantum computers. The key is to identify problems where the unique strength of quantum mechanics can give quantum computers an edge. Okay. Alright. Again, quantum approximate optimization algorithms. Something to read tomorrow. So tomorrow, instead of moving forward, especially with QKits, I want to read those papers and understand these concepts. NISQ, noise intermediate scale quantum machine learning, quantum neural networks, quantum supervector machine, quantum principal component analysis, and quantum key means clustering. These are the concepts to learn tomorrow. Today, a lot was learned. Today, a lot was learned. And still, there's so many. This is so broad that I need to go everywhere to start drawing a path. I have two options here. I can draw my own path, or I can look for an expert's suggestion on the path. Or I have a third option, which is asking AI what path I can take. So I have a conflict here. In my past, I lost tremendous amount of time reading about concepts that wouldn't necessarily be useful for me. I remember when I started working 15 years ago, I used to read RFCs. I remember knowing the SMTP RFC and the IPv4 and IPv6 RFCs. Specifically IPv4, I remember knowing the header by head. I've never used it. Well, I won't say that wouldn't be useful. Actually, it was quite useful for me to understand concepts on, say, Nmap, Nmap is a tool to map open and closed ports in remote machines. It is used for hacking. And knowing the API RFC, which I barely remember, wasn't necessary, but possibly helped in understanding the low-level approach of safe fingerprinting. The thing is that took me much time that I could probably address to more relevant stuff. And my fear is that I follow the same principle here, and I'm going to learn about concepts and go deep inside concepts that might not be that relevant at all. But I'm 15 years older, and I believe, I hope so, I'm better at reasoning than I was 15 years ago. So these are the arguments that are pro on me tracing my own path. Following some expert's path is the principle of being schooled by someone, which is great, because the goal of learning is that we don't stumble in the same pitfalls others have stumbled before. But there are two things. First, I don't believe in the concept that we should not reinvent the wheel or rebuild the wheel. I think, especially when we are starting to learn concepts, to understand stuff, I believe we should definitely rebuild the wheel, because that aids us learning base concepts. In coding, I have never coded a sorted algorithm, for example. I don't think I needed it. But I did create a flow algorithm, for example, from scratch. And I have created an ORM from scratch. Those are applications, those are more applicable to my area of knowledge and say engineering than a sorting algorithm. I'll never choose a sorted well, at least I never choose a sorted algorithm instead of another. I don't need to. All the good that I've been doing so far, that problem has never posed, so I don't think it's necessary for me to know the difference between one and other algorithms, which I don't. But it's important for me to understand the various flows, patterns, and algorithms that exist, because that is relevant for a product that I'm currently building. Even though I don't use that my code anymore because it was not good, and I can use a mature open source code, especially namely Airflow, Apache Airflow. It was useful for me to understand what's behind it. And when one follows the path of an expert, they lose this experience. Fact that they move faster And that's important when speed is relevant. I believe this is not the case. I have no urgency in knowing this. I think this is an area of science that is pretty immature still, yet. And I have no FOMO for it. I'm pretty much on time to learn about it, to experiment, so that when it became a thing, I already know a couple of things. And that's my goal. So I have no urgency in it. The other argument against following an expert path is that it can be outdated. As I've seen so far, these concepts do not move as fast as AI, for example. AI moves quick, indeed. A paper published, say, 2 years ago is already outdated. It's not obsolete, but it's outdated. And though I don't need to be in the top of the wave, I definitely don't think that looking for earlier version documentation is, say, smart. Well, it's smart, indeed. It's not the best word. But what I mean is that I think it's smarter to pick the most recent documents or publications, I mean, and then look for concepts in older documents. My cat is playing with the carpet. Tico, as done for quantum approximate optimization algorithm. I've read documents that are pretty new, and then I looked into a document that is 10 years old. So I believe this fear is funny, possibly related to FOMO, which might not be applicable in quantum computing because, as I assessed so far, it doesn't move as fast as blockchain or AI, which are subjects that I've been working for the past 7 years, I've said in the beginning. The third option is using AI, LLMs, to draw that path. Specifically Gemini, which can assess this tremendous amount of knowledge that GPT still can't. Even though the output is better at GPT, Gemini is better at RAGing, because that's the Google power. So yeah, I don't know. I'll probably have a mix of them. I don't need to be specific to any of them. Using AI, using LLMs to look for concepts and learn about concepts as the QA way is possibly a way to go. And it's a merge between tracing my own path and using AI for it. I kind of I just understood. I'm trying to make sense of my own emotions and thoughts. I just understood that I have some resistance to follow an expert path, and that is probably some arrogance from me to do that. But I don't care. It's my own path, and I have no urgency in this. So I don't know. I'll probably follow the three of them, regardless. So far, this is the first day. A lot was learned so far. A lot is need to be learned tomorrow. And tomorrow I'm here again at 10 o'clock. Yeah, probably not tomorrow. Because tomorrow is Saturday. And I'll probably want to drink a couple of beers tomorrow. At least at 10 o'clock. I might have come sooner. And probably that's even smarter to do, because coming sooner will allow me to be more focused, as at 10 o'clock I'm already tired. I don't know, tomorrow is a new day. Bye bye. Have a good day. And now I need to close this. To close this session. And it's done like this. Bye bye.